Good morning, everyone. Today I am going to present a seminar topic on Introduction to Unified Power Flow Controller and its operation. And these are the contents that I am going through. And next, basic principles of the UPFC modes for the UPFC and operation of UPFC, that is connected with UPFC connected at the sending end, and next one is UPFC connected at the receiving end, and further conclusion with references. And starting with introduction, since the concept of flexible AC transmission system, that is FACTS, it was introduced, a family of power electronic equipment has emerged for controlling and optimizing the flow of electrical power in power transmission lines, like line outage, congestions, cascading line tripping, power system stability losses. These are the major issues where capability and utilization of FACTS are noticed, and representative of the last generation of acts devices is the UPFC. This UPFC is a device which can control simultaneously all three parameters of line power flow, line impedance, voltage, and phase angle. Such a new pack device combines together the features of two old pack devices, that is the static synchronous capacitor STATCOM and the static synchronous series capacitors, that is SSSC. And this UPFC first is proposed by Guge, and it is the most versatile FACTS controller for regulation of voltage and power flow in a transmission line. And it has consist of two voltage source converters. One is shunt connected and other is a series connected. And it has the DC capacitors of the two converters are connected in the parallel. And this is the basic operating principle of the UPFC. Here you can see that one reactor is connected is a shunt, on another connected is a series. We have two intermediate transformers and two voltage source converters connected across the series capacitors. If the switches 1 and 2 are open, then two converters are work as a STATCOM and SSSC, controlling the reactive current and reactive voltage injected in the shunt and series respectively in the line. If the switch 1 and 2 are enabled, the two converters to change real power flow between the two converters, and the active power either absorbed or supplied by the series connected converters. These are the basic operating modes for the UPFC. Shunt inverter, in that VAR control mode, automatic voltage control mode. In second one, series inverter, we have direct voltage injection mode, phase angle shifter emulation mode, line impedance emulation mode, and fourth one is automatic power flow control mode. And the third one is standalone alternative modes. These are the basic different operating modes for the unified power flow controller, that is UPFC. And we have now this operation of UPFC, that is first one is the UPFC connected at the sending end. Here you can see figure. Single line diagram. We have sending end voltage, receiving end voltage, line impedance. So provision of energy or power source at the DC bus of a triple SC enables the control of active power as well as reactive power flow in the line. So starting with the, we have sending end voltage VSC, that is equal to V at an angle of delta by 2, and receiving voltage VR is equal to V at angle minus delta by 2. And the figure like single line diagram shows that triple SC connected at the sending end of the line. Let if the injected voltage VC, that injected voltage VC, it can be expressed as VC cap. VC cap, it is not denoted as VC cap, that is VC equal to VC at an angle beta, that is equal to VP plus JVR at an angle minus phi. That is we called as equation 1. And we have equation for active and reactive power injected at a line, that is PR equal to V square sin delta by XL plus V into VP by XL sin delta by 2 minus phi plus V into VR by XL cos delta by 2 minus phi. And for reactive power injected minus QR equal to V square by XL into bracket 1 minus cos delta minus V into VP by XL cos delta by 2 minus phi plus V into VR XL VR by XL into sin delta by 2 minus phi. That is equation 3rd. From these two equations, PR and minus QR, we have simplified equations for PR, active power PR equal to P naught plus V into VP by XL into sin delta by 2 minus phi plus V into VR by XL cos delta by 2 minus phi, where P naught is the V square by XL sin delta. And for reactive power minus QR equal to Q naught minus V into VP by XL cos delta by 2 minus phi plus V into VR by XL into sin delta by 2 minus phi. Here Q naught is equal to V square by XL, that is V square by XL into 1 minus cos delta, where P naught and Q naught are the active power and reactive power in the absence of the series converter. And here sin phi equal to Vp by 2 V into sin delta by 2. From the equation we have Vp equal to Vc cos of beta plus phi and Vr equal to Vc of sin beta plus phi. That is equation 8 and 9. Substituting these above equation 8 and 9 in the equation 4, we get PR equal to P naught plus V into Vc by XL sin delta by 2 plus beta and minus QR equal to Q naught minus V into Vc by XL cos delta by 2 plus beta. From equation 10 and 11, we can express that active and reactive power PR minus JQR equal to P naught plus JQ naught plus V into Vc by XL into the e raised to j into bracket delta by 2 plus beta minus pi by 2. This shows that for a constant value of Vc and beta varying over 360 degree, the locus of PR and JQR describe a circle of radius, that is circle of radius V into Vc by XL and having a center at P0 and P0 at Q0 in the PQ plane. And for a specified value of delta, P is maximum, that is when beta equal to pi by 2 minus delta by 2. In that condition, P is maximum, active power is maximum. Therefore maximum power P max equal to P0 plus V into Vc by XL. Next we have the UPFC connected at the receiving end. The figure shows the single end diagram and or equivalent circuit, line supplying a load through the UPFC, and we have phasor diagram. Here if we assume that UPFC is connected at the receiving end of a line supplying a load and reactive powers supplied by the shunt converter improves the power factor of the apparent load to unity. In other words, you can see that in phasor diagram that I is in phase with the V voltage. Therefore, the power transmitted over the line is given by P equal to V, that is equal to V into bracket IL plus IP, that is the equation 1. Here V and IL are the obtained from the phasor diagram. As V equal to Vm minus Vp, that's equal to E into cos delta minus Vp, that is equal to N E into cos delta. Here IL is equal to 2E sin delta by x, where N is equal to V by Vm, that is equal to Vm minus Vp by Vm, and N is less than equal to 1. Here we have a note where Vp is considered as a voltage drop. Vp is considered as a voltage drop, so that N is less than equal to 1. Therefore, I is equal to IL by N. Hence, we can derive that power power flow active power P equal to x e square by x sin 2 delta, that's equal to 2 into, that is P equal to 2 P naught. The power flow is double the value without the injection of VR. Therefore, the UPFC in this case can be replaced by triple SC injecting VR to enhance line current, and STATCOM injecting IR to compensate for the reactive current drawn by the load. So, conclusion. So here I conclude that in power system transmission, it is fascinating to take care of the voltage magnitude and phase angle and line impedance. Therefore, to manage the power from one end to a different end. This idea of power flow management and voltage regulation is applied using the system, and finding out the results have given the sign that UPFC are very helpful once it involves organize and maintain the power system. And these are the references, that is Narayan and Hingorani, Leslo Gugi, Understanding Facts IEEE plus 2000, HF Wang, UPFC Analysis, and NG Hingorani, High Power Electronics and Facts IEEE. Thank you, thank you everyone.